Words for today are superposition and interference. Superposition is just what it sounds like. It answers the question, what happens when two waves collide, namely when they're superimposed on each other. Interference is another word for superposition. It's what happens when waves collide. Find something on which you can make waves, like a chain, a slinky, a necktie, or a rope, and send wave pulses down to meet another. You'll have two wave pulses facing the same way. See what happens when they meet. You'll notice that the wavelength will only stay the same if you're not in a situation where friction is doing work. In our house, we were making waves on the carpet, and quite a lot of mechanical work was done by friction as the wave traveled down the carpet, losing energy and wavelength and height and just about everything else. But if you're making waves in the air, friction won't be much of a problem. You'll see that the wavelength and speed basically remain the same, and the only thing that changes is the amplitude. Try two waves facing the same way, see what happens. Then flip one of the waves upside down. See what happens when both waves are facing different ways. When you're done, you can press play to see our results. Two waves in the same orientation, both facing this way. Focus on the middle where the waves meet. 3, 2, 1, go! What happens to the amplitude in the middle where the two waves meet? Second exercise. Two waves of opposite orientation, one going this way and one going that way, of approximately the same size. Again, focus on what happens as the waves collide. 3, 2, 1, go! Right in the middle, as they collided, what happened? We'll try this demo again, and we've got one more question to answer. That is, when the waves hit each other, do they bounce off each other like football players, or do they pass through each other? I'm going to send a big wave facing this way, going that way. You're going to send a small wave facing this way, going that way. See whose wave comes to whose hand. 3, 2, 1, go! Which wave arrived at you, the big one or the little one?
Big one.
Ah, so they didn't bounce off each other, they passed through. Experiment 3, a fixed end. Fixed means it's fixed down, means something's holding it. And what is rule number 1 through 8 of the physics class, Slinky?
Do not let go of the slinky. 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 8 times.
All right, fantastic. So, given that we have someone taking personal responsibility for not letting go of the slinky, we know that end is definitely fixed. Look at what happens to a wave when it hits a fixed end. What changes after it's hit your hand?
The way the wave goes.
Yes, not just the direction, not just from forward to backward.
The way the wave went.
It's upside down. When it came back, it was upside down. You can do an unfixed end yourself most easily by simply standing on a chair and holding the rope you're making the wave on down. Nobody will be holding the other end. You'll see how the wave behavior is different if nobody's holding the other end. First key question is it going to flip upside down or not? You've got a slinky, you can make great compressional waves, but you won't get any better high contrast than this fabulous wave generator at the physics classroom that we have in our classroom if it only weren't closed for COVID-19. Check it out. Here comes the wave. There it is at the end. Does it flip upside down? The next question is why? Why? Why is it if one end is fixed, the wave comes back upside down, and if the end is not fixed, it comes back right side up? The key is the concept of wave interference. Both of these questions skip the most important part of what happens to the wave, namely what happens right here as it hits the end. The free end is very, very easy. There's absolutely nothing in the way at the free end. Pause, go back in the video, and check what happened to the amplitude of the wave as it hit the free end. Compared to the wave when it gets back, you should see a very dramatic difference, just as dramatic as the difference in the wave you made yourself. If you see the end lashing out, if the person holding the cell phone camera or the person holding the other end of the necktie has to jump out of the way to avoid getting slinky whipped, you're definitely looking at the right part of the wave. Now, ask yourself, if the amplitude is just about doubling at the end, is that constructive interference or deconstructive interference? Pause the video for a good long while, get on Skype for Business, text some of your classmates, and figure out What's happening at the unfixed end, at the free end, that would be causing constructive interference? Here's the deal. Constructive interference requires two waves. At the moment, we see only one wave pulse. Once we've figured out what's going on for the unfixed end, we should, by process of elimination, to be able to figure out what's going on with the fixed end. Pause, confer, and come back when you're ready to check your answer. The most important part of this question is the hunt for the two waves. If we can find two waves in this picture, we will know what it is that's interfering. Wave comes in, wave turns around, wave comes out. Where's the second wave? To answer this question, we here at Vex Labs, homebound for COVID-19 in March of 2020, have called upon the Dreifuss family, the family from pioneer to present with the most number of CJHS students, alumni, and current RZJHS students under one roof. Thank you to the Dreifusses for the demonstration. Let's try that again. Here we have our incoming wave. Crest, trough, crest, trough, crest, trough. You can see 5 crests and 4 troughs. The wave is hitting a boundary, an unfixed end, nobody's tying them down, and reflecting off of it. You know about this, you call it wave reflection. Let's look at what happens to the individual crests and troughs. The first crest hits the wall, reflects off at the same angle it went in, and turns around. Second wave, third wave, freeze frame. Hold on. We have one wave at the wall. We have one crest, one trough going outbound, one crest, one trough going inbound. Why haven't the last two members of the family turned around yet? Well, that's easy. They haven't turned around yet because they haven't reached the wall yet. The first two Dreifusses have turned around long since because they were in the front of the line. They have turned and they're on their way back already. That means if they don't have a whole room to dance the coronavirus conga in, if they only have one slinky or one rope or one medium to go through, these two crests are going to be occupying the same place at the same time. These two troughs are going to be occupying the same place in the same time, and these two crests likewise. Their two waves that we were looking for are the front half of the wave, which has turned around already, and the back half of the wave that hasn't turned around yet because it hasn't hit the end of the medium yet. The first half of the wave that has already reflected meets the back half of the wave that has yet to reflect. The two of them are facing the same way, so of course the amplitudes add. Two amplitudes, front half and back half, add for just an instant to make a double-sized amplitude, but as soon as the back half turns around and is on its merry way, you have the whole wave once again. Something about this must be happening on the fixed end. The difference is, with someone or something holding the fixed end down, the fixed end cannot physically jump up and down like this. Well, process of elimination says that if this is constructive interference, then no prizes for guessing which one this must be. Check it out. If you add the front half of the wave that's already reflected but upside down to the back half of the wave that's still on its inbound journey, what do you get when these two overlap in the same position at the same instant? They have to be identical in wavelength, frequency, and amplitude because they're halves of the same wave. Does it, by any chance, subscribe to the constraints of the problem whereby this point is absolutely fixed and cannot move? If you've satisfied yourself that flipping the wave upside down as it reflects off the fixed end satisfies the destructive interference rule and the fixed end, use Newton's third law to explain why, if a wave coming in pushes up and forward on your hand or on the bolt, well, finish the sentence and see what happens to that wave.
Atse shiti om dim, atse shiti om dim, atse shiti om dim, atse shiti